sorry, only read, it is wrong. But in case of NAND RAM, all the word lines are by default connected to supply. That means all the transistors wherever present are by default on. As you can see on the top side of this ROM array, it is connected to VDD through some permanently on transistors. PMOS transistors, grounded means they are on. So one side of that they are permanently connected to supply, the other side is connected to ground, and outputs, as you can see, the bit line outputs are not taken from either end, it's taken from the top of the array below those transistor connecting VDD. It's like a pseudo NMOS logic gate. Each column is acting like a pseudo NMOS NAND logic gate. That's why it's called NAND ROM. So by default, all the word lines are active. So by default, that bit line 1, 2, 3, and all 4 all are connected to ground. So by default, everything will be 0. However, activation of word line in this case means that, let's say I'm reading this one. This line will be turned off. That means power will be disconnected. It will be grounded.
Because it is PMOS and
Hmm?
why it will be turned off? Because it's PMOS, they are considering.
No, because the NAND logic works in reverse. NAND ROM works in the reverse logic than NOR and OR ROM. In NOR and OR or diode ROM, we activate the word line that we were trying to read. Here, by default, all the lines are connected to supply. We deactivate the line or disconnect the line from the supply, the line we want to read. Let's say we want to read this line. We disconnect this from the supply, what will happen? This transistor will be turned off because it is not getting supply anymore. This transistor will be turned off. So the line is disconnected from the ground. The only connection it has is through those two weak PMOS transistor to the supply, like PMOS logic gate. So bit line 1 corresponding to this and bit line 2, bit line 3 corresponding, will read 1. Why? Because they are connected to supply, because they are not connected to, so they are disconnected from the ground. So by turning off word line 2, I am disconnecting these two transistors from ground by turning them off, thereby providing connections to VDD only, no connection to ground. So bit line 1 and bit line 3, for this case, will produce a 1. So the information that is stored in this line will be 0, 1, 0, 1. Presence of a transistor means 1. Absence of a transistor means 0 in NAND ROM. But one thing we have to remember, NAND ROM works in the reverse logic of OR and NOR or diode ROM, previous 3. Here default all the lines are activated. So default all the bit line will produce a 0. The moment we want to turn on a particular, let's say we want to read this line. If we deactivate this line, read means we deactivate this line, but nothing will happen in any of those intersections. All those transistors are by default on, so all the bit lines are connected to ground, so it will produce 0. So information here will be 0, 0, 0, and 0. So if you just look at the circuit diagram compared to any of these two, this is much cleaner, no intermediate contacts, no parallel VDD and ground, much cleaner. So this should be the design choice. However, the problem is, as you can see, the transistors are embedded inside the bit line. What if you have a 10 by 10 array? In a particular column, the bit information you are storing all ones. So you will have 10 transistors embedded in series inserted into the bit line. for any design, more than 4 transistors in series, whether it's a logic circuit or memory circuit, is not recommended. Because that long series chain path will introduce tremendous amount of delay, like those Elmore delay segment. More segment it will add, so it will increase the delay in exponential order. So that's why larger array of ROM using this principle is not recommended, because depending on what data you are storing permanently, you may end up some column with fully populated long series chain of transistors in series. So that's why it is not recommended for complex high density design. For high density ROM design, these are the 2 design choice as we mentioned. Yes.
So on the top and bottom of each of these diagrams, you've got a series of transistors there that are permanently on. Why would we not just use a wire there? Why do we need transistors there?
So the question is, because if we connect directly to the VDD, then we will not have this zero and MOS logic operation that when it is grounded, ground connection will be stronger than those. So those VDD will try to keep bit line 1, 2, 3, 4 charged, where whenever a connection to ground is established, it will try to discharge to produce a 0. But if we directly connect it to the VDD, it will never be able to make a downward transition to produce 0. It will be permanently VDD high, so there cannot be any change. But if you remember, in CNO and MOS logic gate, it's a ratio design. That permanent pull-up transistor, which is PMOS grounded, it's a very weak transistor. Whenever we need a high to low transition, that pull-down network transistor, so here all this transistor is acting like pull-down network, they must be able to quickly bring it down before that weak PMOS can charge it. So there is a ratio problem, but without having this ability to bring it down, we will not have any way to change the logic values in bit line 1, 2, 3, 4, 0, 1, 2, 3, 4, right? So that's why we need to have a switch between the output node and the supply. Now one of you asked, why it is permanently grounded here? We need a switch no matter what. One option is, while I can avoid the ratio condition when I'm establishing a ground connection, why not turn off all the transistors so that we don't have a competition, right? So bit lines will have only ground connection, right? So, but in this case, we are not able, we don't want to turn off, because in this case, the default value for every node is that all the transistors should be 1 and it should have a connection to VDD and the ground, and ground connection should be stronger, so it will be a downward movement every time sense amplifier reads it, it will see that it is discharging, so it will read 0. And when we activate certain line, if there is a transistor, that transistor will be turned off, ground connection will be disconnected, only connection there will be left through those PMOS transistor to VDD, so that corresponding bit line 1 and bit line 3 for these 2 cases can produce a 1. So we need to have a switch over there, whether it's a transistor switch, any other switch, to be able to establish, and if needed, disconnect the connection. Now, controlling those switch PMOS transistor, here in these 2 cases we have shown that it is grounded. In this case we have shown that it is a bias. Actually, the general is it's a bias voltage. In case of PMOS, those, in the way it is designed, those PMOS should be permanently on, because it is kind of a CNO and MOS design. That's why we connected it to the ground permanently, because that's where this bias voltage, required bias voltage is 0. But we can also keep it open like this. Whenever we need, we will supply. Here in this case, all those NMOS transistors should be on to establish a connection to ground. So this one should be VDD. So in general design, we can just draw a line through all the PMOS transistor and write bias. Now we can convert any of this into dynamic gate. How? We can force the bit line to be in the floating state by connecting, instead of bias, I put a pre-charged clock. So in one stage it will be pre-charged to a default value. In the next half cycle this will be turned off. All the bit line will be maintaining its whatever default value in floating state, and then upon activation of the bit line it will see changes depending on whether it is connection to ground or VDD, and bit line will correspondingly produce the value like any dynamic logic gate. So this is our common bias point. I can control it with a clock signal, then it becomes same NOR ROM dynamic version, same NAND ROM, I can basically convert it to dynamic version. Instead of connected to permanently ground, I can connect it to the clock, right? This one we have already shown. Instead of connecting to ground, connect all the way everything together to a clock, it becomes dynamic version. This is seed one was static version. Same thing, I can connect it here a clock, right? So that bias voltage can be VDD or ground. Since here I know that it is kind of in non-ROM and NAND-ROM, every column is implemented like a CMOS logic gate. That's why the upper side, the VDD side, is connected to the switch PMOS, which is permanently grounded to keep it on all the time. But here, the way it is designed, we may turn on and off this device connected. So we can connect all the way to permanently VDD if we want to keep them always on, or we can say general bias. But I am showing just all options here. But typically, this connection should be your bias voltage. It can be VDD, it can be ground, or if you want to make it a dynamic floating ROM, it can be a clock signal. So these are kind of relative comparison between NOR-ROM or OR-ROM and NAND-ROM. Why it is not preferred? Since here transistors will appear in series, longer the column, more transistor will appear in series. Whenever there is a series connection, you cannot use minimum size transistor. The lower end transistor has to be larger and larger because they will carry more current. The top one close to output can be smaller. It's a staggered design. But here in NOR-ROM, no two transistors will appear in series. Every transistor is independently appearing in parallel to the bit line. So in every position, in its own position, every transistor is doing the switching, charging or discharging by itself. No other transistor is appearing in series. So although it looks like simpler, it is saving lots of intermediate ground and supply connections, lines and contacts. But this one, the types of transistor we use, the size, number one, it is a ratio design. All those transistors must be significantly larger than this one to maintain the ratio design principle. Plus, in series, those transistors will be progressively larger and larger as they go down the chain. So you can never use minimum size transistor in this area. But in ROM, NOR or ROM, every transistor is by itself in its position, so you can use minimum size transistor in or NOR ROM. So the overall design will be much more compact and high density, and ability to use minimum transistor also saves power, because lower the size of the transistor, lower the parasitics. Also, lower the parasitic means higher the speed. Lower parasitics, lower resistance, higher the speed. Also, the long series chain of transistor will slow down the device. So, in terms of reliability, in terms of energy efficiency and speed, this is much better. Yes.
You mentioned that the NAND requires a ratio design near to the NOR.
Yeah.
Why is that?
Because the way the NAND is designed, first of all, we need to, that's what we're explaining, why we need this permanently on switch here. Because we want to be able to change the binary bit whenever we are reading this value from default to something else. So all the lines are by default on, all the transistors are by default on. So on one side they are connected to ground, on one side they are connected to supply. Why we want to make it ratio? Because default we want to achieve all zeros inside the array. And then when we activate a line, that means when we disconnect the line, in this case, we want to read 1 here, but 0 here. How we can read 0 here? We can only read 0 here if this line can pull it down at a much faster rate than this one can charge it. If we remove the switch, directly connect it to the supply, then there is a short between supply and ground, and it's a meaningless. If it is an electrical, if you do not have control on this node, then you don't get any meaningful output. It's just a shorted wire between supply and ground. So if I want to use this as a logic node or memory node, information reading node, I have to have the ability to change it. Now, one way is to put a clock switch here, connect it and disconnect it whenever needed. There is one option. The other option is turn it on permanently, but make this transistor or this line stronger than this transistor, so that whenever this is on and this is connected, this one can discharge at much faster rate, this one can charge. So the sense amplifier connected here will see that it is going down, and it will read a 0 for this intersection, this intersection, this intersection, this intersection. But for this intersection, when I deactivate this transistor is off, it loses connection to ground, it can charge this node to 1, sense amplifier will read a 1. So that's why we need to provide a switch. That switch can be a grounded switch like CNO and MOS, or that switch can be a clock switch like a dynamic logic gate, or that switch can be a general bias signal. In some case it can be supply, it can be ground, depending on which one you are using, right? So I'm just showing in all these three designs all possible scenarios. But the message is you need to have a switched control between the bit line and the supply and ground line. You cannot just short them. It becomes a short circuit, then you don't lose the ability to control the voltage of the output. So the problem with this is ratio design, as we mentioned in lecture 4. Ratio design is always inefficient. You have to sacrifice a lots of area to make those transistors bigger and stronger, and it will always continuously consume static power, because Default, there is a connection from supply to ground. So it will area efficient, energy efficient, and also less robust. So that's why this design is not used. So we basically use mostly NOR-ROM or ROM depending on the density of ones and zeros. One of the common feature of any of the ROM cell is none of this ROM cell is allowed to make a full 0 to VDD or VD to 0 swing. At the output, with the bit line output, whether you take it from here or here, it will always feed through a sense amplifier. Sense amplifier will see whether it is going up or down, and it will produce a 1 or 0 based on the change of the voltage. So that delta voltage swing, how quickly a sense amplifier will kick in, and for how smallest change upward and downward, a sense amplifier can produce a correct 1 or 0. That depends on the efficiency or sensitivity of the sense amplifier. You don't want to make the sense amplifier too sensitive, because then if a slightest noise takes the note slightly up, it will read there is a 1 coming, but probably it is not a 1. So you have to allow that delta V to change upward or downward for certain amount of time. Let's say 20% of VDD, 25% of VDD, or 10% of VDD, depending on the sensitivity of the sense amplifier, so that inadvertently you don't latch on a noise. So these are the design considerations. So that's all with the ROM, as I said. So we have seen 4 different designs of ROM: diode, OR-ROM, NOR-ROM, and NAND-ROM. And then we can make them pseudo and MOS like permanently grounded. We can make them clock control dynamic, or we can control them using a simple bias voltage, and then we will apply supply or ground depending on the type of ROM we are talking about. Next, we are going to move to static RAM. So in this slide, we just covered this one. Now we're going to jump to RAM. RAM, although this one is random access, this one is random access, but random access memory is reserved for the term random access read-write memory. The memory where you can not only read, you can also rewrite, erase at any way you want. Very versatile memory, and they are grouped into 2 classes: static RAM and dynamic RAM. Today we are going to talk about static RAM. The foundation of entire RAM industry. Entire RAM industry started with the introduction of the first, and still today the most popular static RAM cell design is called 6T RAM cell design. So whenever people mentions RAM design, they will mention a terminology. Is it a 6T design? It is an 8T design, or 7T design, or 9T design. T stands for transistor. If the RAM cell requires 6 transistor, it's a 6T design. If it's 7 transistor, it's a 7T design. There will be some 8T design, right? But standard static RAM across the board, the basic cell of any SRAM you use day to day, these are based on 6 transistor design. This is the industry standard 6T transistor design, the very popular SRAM cell. As you can see inside this SRAM cell, what we have? We have 2 transistors connected back to back in positive feedback loop. Nothing but a simple bistable multivibrator circuit. As you can see, M1 and M2 constitute one inverter, M3 and M4 constitute another inverter. As you can see, output of the first inverter, forget about these two, is connected to the input of the second inverter. Input of the first inverter is connected to the output of the second inverter. Input of the first inverter is connected to the output of the second inverter. So it is producing a 2-inverter bistable loop. So a static RAM is nothing but a bistable multivibrator circuit made of 2 inverters connected back to back. However, in ROM, we do not need any access point to this point. These are permanently hardwired. As soon as we design it, informations are permanently hardwired. You cannot change. So we do not need to access any of those intersections where we are storing the value. But RAM is something we want to write, rewrite, read at any way we want, and as soon as the system is turned off, everything is wiped out. So we need the access to the nodes where informations are stored. Informations are stored in this common node and this node, right? If I inject a D here, this D is stored here and here, D prime is stored here, right? So these two my information node. I have to have access to those nodes to write and rewrite new information into those memory nodes. So if I call this one, if I call this one as my Q, this one will be my Q bar, right? So if I call this one Q, this one will be my Q bar, right? Here the output is Q and Q bar, right? That's what D latch. So to provide access to Q and Q bar, to change the value, I provided an access transistor with Q node, another access transistor M5 with Q bar node. In regular ROM, we had only one bit line because we are just reading them, that's it. But in static RAM, we have to have 2 bit line. One bit line is called bit line, the other one is called bit line bar. Because static RAM or bistable memory element stores both Q and Q bar. Sometimes we have to read the Q and sometimes we have to read Q bar. Sometimes writing will take place from this to set the value here, or sometimes writing will take place to this to set the value here, opposite from each other. So static RAM requires 2 bit line, one for the signal to read and write and one for the signal invert. Bit line is connected to the node Q through transistor, access transistor M6. Bit line bar is connected to Q bar through access transistor M5. So access and exit through this transistor will be controlled by M5 and M6, and they will be controlled by the word line. So the activation of this SRAM cell means providing access to and exit from this SRAM cell will be controlled by these 2 access transistors, and they will be controlled by the word line. So every static RAM cell will consist of 6 transistors, 4 for 2 inverters, 2 access transistors, and 3 interconnecting lines, 2 bit line and 1 word line. So 60 industry standard SRAM cell contains 6 transistors, 2 bit line and 1 word line. Now let's see how it works. Let's start with the read operation. Let us assume that we have a 1 stored in Q, that means a 0 stored in Q bar. Logically, if I read from this side and see that Q bar is 0, automatically I don't need to read anything. Logic circuit can assume that Q is 1. right? Or if I read from this side, if I see that Q is 1, if the logic circuit needs Q bar, it automatically can assume and interpret that Q bar is 0. So the reading of Q equal to 1 can take place in two different ways. I can access through this, or I can access through this. Reading a 1 is equivalent to reading a 0 here, right? So now let us see, with 1 stored at Q and 0 stored at Q bar, what is my circuit situation? This output is connected to the input of this inverter. If this is 1, M1 transistor is on, M2 transistor is off. M2 is out of the picture. If this Q bar is 0, M3 is off, M1 is on. So in the circuit, as if what I'm having, M1 is 1, there is activated by VDD, M4 as if it is getting a grounded signal, right? Because it is 0. Now I want to read this 1 or this 0. So first thing, I have to activate the SRAM cell by turning on word line. So it will turn on this transistor and this transistor. The moment this transistor is on, at the same time, I am reading now. To read, I have to activate these 2 bit line. Right? The moment I activate this 2 bit line, they are now powered up. And M5 transistor is on, M6 transistor is on. So this node is connected to a powered up bit line. So bit line will inject charge into this node Q bar. Right? But Q bar is 0. You do not want to destroy the value while reading that 0. You want to keep it at 0, right? Because during the read cycle, you just read, you don't change the value. But the moment M5 is on, bit line is powered up, it is injecting charge in this direction. Why? Powered up means it is at high voltage. This one is storing a 0 means it is at low voltage. So the charging will take place this way. So what will happen as we charge this? Q bar node will go up. If it goes up too much, it may lose the value 0. So but good news is, this one is on and this side is connected to ground. So whatever it charges, M1 should discharge it so that Q bar does not accumulate enough charge to flip the bit from 0 to 1. So to make sure that while reading 0 at Q bar, you do not accidentally flip the bit from 0 to 1, what I have to do? At the rate this charges, this one should discharge it at a much faster rate. So M1 as a transistor must be stronger than M5. So that whatever M5 injects from bit line bar to Q bar, M1 quickly discharges it to the ground so it does not accumulate enough charge to change the 0 bit. But so that's why it is drawn larger. So M1 should be larger than M5 in size, stronger, so that it can discharge it. So first thing is, while reading, I do not want to change the value. So by making it larger and stronger, this side is connected to Q equal to 1, so it is on. It will discharge it quickly at faster rate than it is charging. So Q bar is protected at 0. But now, how reading will take place? Bit line bar is originally powered up at the beginning of read cycle. Now it sees a discharge going down. So sense amplifier, which is connected this side, it sees that the moment bit line bar is powered up, it is going down. So it will read that a 0 is stored here. On the other hand, bit line also is powered up at the same time. But nothing will happen here. Why? Because this side, Q is equal to 1, and bit line is powered up, means it is connected to supply. So excess transistor M6 has 1 and 1 on both sides. So no charging and discharging will take place. So we are reading Q equal to 1, but nothing is happening on beat line. But this one we'll see a discharge, a down one. So reading 1 is actually taking place on the other side. By reading a 0 here, this sense amplifier will see the default value of 1, nothing will happen, so it will deliver 1. As you see, the read operation, reading 1 is taking place from the other end by reading Q bar equal to 0. So two things. How do we read 0? We read 0 by observing a downward discharge or downward change of voltage at one of the two beat line. Then we read 0. Sense amplifier will see that we are reading 0 here, and the other end by default will be 1. If we read 0 here, then this end will be 1, right? Because they are opposite, Q and Q bar. Then how do we protect this node while reading 0 here? So that it doesn't accumulate charge, we make this transistor stronger and bigger compared to this one. So static as SRAM cell, always static design by default is a ratio design. Ratio design means whenever you have to make certain size ratio, you have to make one stronger than the other, larger than the other. That's called ratio design. So M1 has to be larger. So we correctly read without. So now, to correctly read without accumulating much charge here, we have to maintain a size ratio between M1 and M5. That is a very, very important design parameter in static RAM design, and that is called cell ratio. Cell ratio is the size ratio of M1 and M5. So that's common sense. What should be the value of cell ratio? For this SRAM cell to operate correctly, that means without accumulating much charge here, the cell ratio should be greater than 1, because this one should be larger. Cell ratio is the ratio of size of M1 with M5, right? So you as the designer, you have to make sure that while reading 0 here, it does not accumulate much charge above 0. You have to make this larger. So larger the cell ratio, faster will be discharge, lower accumulation you will have here at Q bar. So Q bar will be protected at 0. So cell ratio, one of the important design parameter in SRAM cell design. Now, let's look at so this is like a plotted cell ratio with voltage rise at Q bar. You don't want that voltage to be raised above and PP2. So larger the cell ratio, voltage accumulation at Q bar will be smaller. And we want to keep it as small as possible so that you don't lose your 0. So ideally, this is where we want to make it cell ratio, because depending on what is the threshold voltage of the transistor or lower noise margin, we want to select a very large cell ratio. Now let us look at the right operation. Initially, let's say we have 0 here, we have 1 here. We just explained how to read it. Now, let us assume that we want to write 0 here, that is flip the bit. That means we want to write 1 here. So initially, 1 is stored at Q, 0 is stored at Q bar. So this is my transistor on-off condition, right? From this we know that. So this is my transistor on-off condition. Now I want to write a new pair of values into Q and Q bar. Q should become 0 and Q bar should become 1, because I'm writing a new value. If I write same value, nothing will happen, it will just stay as it is. If I want to see how it will react when I'm trying to write a new set of values. So first activate the word line, These two access transistors are on, providing connection to bit line. Now, the value you are trying to write, you have to deliver those correct value to bit line and bit line 1. It was originally 1. I want to write a 0 here, so I have to supply 0 here to Q. It was originally 0. I want to make it to 1, so I have to supply 1 through bit line 1. So I will deliver 0 here, 1 here. Right? So now, the moment it is turned 1, this is originally 0. Bit line will inject charge into Q bar. Now what do you want? You want Q bar to raise up because you want to convert it to 1. But the problem is, in previous slide, we already made it very large. So as I am injecting any charge to convert it to 1, nothing is staying there because this one is very strong. It is discharging. So writing 1 cannot be done here. I have to look up this way. What is happening here? The moment 0 is supplied here, M6 access transistor is already on upon activation of the word line. So this Q, right, is now connected to 0, so it will discharge. Right? But the problem is, with initial Q, Q bar is 0, and that keeps this M4 is on. So M4 will try to inject charge into Q to keep it at 1. M6 with newfound connection with 0 will try to discharge it. So now there is a race between M4 and M6 while you are trying to flip the bit from Q1 to Q0. Because that M4, because Q bar is initially 0, that is on, providing a connection to Q to VDD. Now you delivered 0 here. On the other side of M6, it is time to discharge it, flip it to 0. So between M6 and M4, there is a competition. But you want M6 to win because you want to flip the bit. So M6 must be larger and stronger in size than M4. So the rate M4 will discharge, M6 will, the rate M4 will charge, M6 will discharge it much faster, and at one point it will go below the threshold and it will flip the bit. The moment it flips the bit, automatically this one will be flipped. If this one is flipped, this transistor is off, then M6 can take it all the way down to 0. But to make sure that it can take it all the way down to 0, and at one point M4 is turned off by flipping this one, we have to make sure that M6 is much stronger and larger than M4. So now we introduce another very, very important design parameter for SM that is called pull-up ratio. M4 is trying to pull it up, M6 is trying to discharge it to flip the bit from Q1 to Q0, and the pull-up ratio is defined as ratio of M4 to M6. Since M6 has to be larger and stronger, for the design to be correct, pull-up ratio value must be less than 1. Pull-up ratio value must be less than 1, otherwise you cannot discharge the Q quickly enough to flip the bit. So pull-up ratio is the ratio of M4 over M6, and since M6 has to be stronger, it is the value of pull-up ratio must be less than 1. It is just showing how quickly the cell voltage will count as we reduce the pull-up ratio. So smaller the pull-up ratio is better. So here we got now, so until now we are explaining read operation when this is 1, this is 0, and write operation when we want to flip the bit. Now if we want to start with 0 here, 1 here, then we will read through this then when we read through this, then M3 has to be larger than M6. When we start with read operation with 0, or next one, when we start with Q equals 0 read operation, we have to read through this, then we have to make M3 larger than M6. And when we start with 0 and 1 as the read, and we have to rewrite it at 1 and 0, we have to do to these two, M2 and M5, and M5 has to be greater than M6. So in conclusion, M5 and M6 in identical position, they are in identical position, they are in identical position. Utilize appropriate pair depending on whether you are reading 0 or reading 1 or writing or reading 1 or 0, right? So what is the conclusion? These two has to be larger than these two. These two must be larger than these two. So there is a progressive sizing. M3, M2 and M4 will be the smallest. M5 and M6 will be in between sizes, and M1 and M3 should be the largest and the strongest in size to ensure proper read and write operation in static RAM cell. So it is a ratio design. As we are selecting the transistor size for correct read and write operation, we have to keep in mind two very important design parameters. One is called cell ratio. Either now I can extend the cell ratio definition. Cell ratio will be either ratio of 1/5 or 3/6. It should be the same because they are of the same size, of the largest size. They are of the same size, second largest size. These two are the same size, smallest size. So the cell ratio can be size 1 versus size 5 or size 3 versus size 6, right? And pull-up ratio should be 4/6 or 3/5, right? 4/6 or 2/5. 2/5 or 4/6 is the pull-up ratio, and it has to be less than 1. Cell ratio by definition has to be greater than 1 for proper operation. So now one of the problem, designers always try to find ways to improve it. So what are the limitations? First advantage. Advantage is static RAM. When you are storing a 1, by default it stores 0 for you. So whenever you need A and A bar in any logic operation, your SRAM cell have it ready for you, both A and A bar. So you just take wherever you want to take it from, Q and Q bar, right? So it can store the signal and its invert simultaneously, and both nodes are available through this bit line, so there is no delay between signal and signal invert you want to read. That is the biggest advantage. And you can read and write in any direction you want, any way you want. So versatility, another biggest advantage. But disadvantage is just for one single binary bit storage, you need 6 transistors and 3 wires, plus supply and ground connection. 5 wires, right? 2 bit line, 1 word line, 1 supply line, 1 ground line, and 6 transistors. So very, very expensive in terms of circuit resource. On the other hand, in ROM cell, you just need 1 transistor per intersection, and 50% case you don't even need a transistor, right? Of course you need ground and supply line you use, but you don't need both. You need either or not, either supply or ground, not both, but you still need 1 bit line, 1 word line. Wiring wise you need 3 wire, maximum 1 transistor in some case, no transistor. So in terms of implementation, this one is much more compact and efficient in the circuit resources, but this one 5 wires, 6 transistors. So, but inside the SRAM cell, what we have? We have two inverters. So designers thought that can we remove some of the internal connections, all those internal wire connections, make it simpler by using simpler inverter. So they tried to implement it using resistive load inverter. Remember in lecture 4 we had ratio resistive load inverter. So lots of connections are moved, but the problem is implementing physical resistance inside the chip is very inefficient, area consuming, power consuming, and it's very highly parasitic prone. So it is not very efficient. Resistive load inverter based SRAM cell, much cleaner, less wire, but it is not efficient and reliable, so they quickly abandoned it. So it was an alternative to standard 60 transistor, 60 SRAM design. But later, IC designer, they not only continued relying on SRAM cell, they started adding additional transistor, introducing 70, 80, up to 90, even 10T design to add additional features, reliability features and performance features into this standard SRAM cell, but those are part of advanced memory design. We will not go there. But the basic static RAM cell design is this one. It is industry standard. In some upgraded design, as I said, some additional transistor will be added here and there to make it 70, 80 or 90 to improve its performance and reliability. But the base core is 60. This type of design, it looks simpler, but it's very inefficient and unreliable. So that is the static RAM cell. But I see industry always evolving. They want to take advantage of the nature of memory operation and the simplicity of ROM design. ROM design is at best maximum. For some cell, you can have one transistor per intersection of quad line and beat line. In 50% of case, you will have no transistor. It is absence of ones and zeros, right? So they wanted to design something simpler than 60. And that was the introduction of DRAM industry. The very first version of DRAM, so what is DRAM? Dynamic RAM. The moment we say dynamic RAM, we automatically know that at some point the memory node will be in floating state and it will be maintaining its memory value across a parasitic capacitance effective at the memory node. In logic, we call it output node. In memory circuit, we call it memory node. The node that will store my binary information. So dynamic RAM will be the RAM which will store the binary information across a node which may be in floating state during the operation. The very first version of DRAM cell that was introduced was known as 3T DRAM cell. By this time you know 3T means 3 transistor. This is the basic design of a 3T DRAM cell. The difference between this one and SRAM cell is, in SRAM you have 1 word line, 2 bit line. In 3T DRAM cell you have 2 word line, 2 bit line. 2 bit line is logical because sometimes we need 1 and 0 to read and write. So we need 2 distinct bit line to read and write 1 and 0. But why we need 2 word line? In SRAM cell, in all ROM cell, only 1 word line was sufficient to activate the whole cell. But in 3T DRAM, one distinction is you need a dedicated word line to activate the read operation. You need a dedicated word line to activate the write operation. So one is called read word line, one is called write word line. Read word and write word line. So constructionally, It is consists of 3 transistor, 3T design, 2 bit line and 2 word line, and good news is it doesn't need any supply or ground connection directly into the cell. It needs supply and ground to activate the line like any other circuit. But inside the cell, it doesn't need any supply or ground because we don't need static connection to maintain 1 for VDD and 0 for ground, right? So supply and ground connections from internal to the cells are eliminated, making it much more simpler. So this 3T design is a significant improvement over the 60 SRAM cell design, because by removing supply and ground you are saving wire tracks plus all the vertical connections going into supply and grounds. So implementation wise, 50% savings of the transistor, 6 to 3. Supply and ground lines are eliminated, but with one addition of 1 extra word line. So this is the construction. Now let us see how it operates. So read operation and write operation. So again, read or write operation also done by 2 different ways. When I am trying to write something, I will deliver the information to bit line 1. When I am trying to read something, I will read it to bit line 2. So I can read only 1 value at a time, write 1 value at a time. So it will lose the ability to store signal and its invert. You can only store 1 or 0, not both. Yeah. So another change is here your Q and Q bar both are simultaneously available, but here you just have 1 value. How do you interpret it? That's a different thing. We'll explain it a little bit. So I have 1 dedicated bit line. If I want to write something new, I have 1 dedicated bit line. If I want to read the node, memory node. The memory node is node X, which is connected to the source or drain of M1 to the gate of M2. That is my memory nodes where information will be stored. So there are some differences. So now let us go back to SRAM. In all the SRAM operation, read and write operation, particularly read operation, why we try to maintain cell ratio and pull-up ratio. Our goal is, particularly for cell ratio, while we are reading it, we don't want to inadvertently flip the bit. Q bar should remain at whatever value it is, Q should remain whatever it is. So the read operation in static RAM cell is known as non-destructive read operation. Memory read operation can be of 2 types. I'm introducing now a new terminology. Memory operation, read operation can be of 2 types. Non-destructive read operation. While you are reading, you are not changing the value. That is called non-destructive read operation. The second type of read operation is destructive read operation. While you are reading it, you are also flipping the bit. So you have to refresh the data back to its original state before you read it second time. So that is called destructive read operation. Write operation, there is only 1 time. You are writing whatever value you want to write, right? So there is no, you are trying to change the value. So that is your motivation to write, right? So read operation once again can be of 2 types. Non-destructive read, while you are reading, you are not changing the value of the memory node. Destructive read, you are changing whether you want or not, the value at the memory node will change. That is called destructive. So SRAM read operation is non-destructive. On the other hand, 3T DRAM cell, quickly it will be clear how it will read. It is a destructive read. Why? We'll explain. It is actually, let me explain here, and it also needs, before we read operation, it needs refreshing of data because it is a dynamic node. This node will be floating in some stage. Noise and other disturbance can distort this value. So this node has to be refreshed periodically. I misspoke. The read also here is not destructive. We have to refresh the data just to save the data from noise-induced disturbance because it is floating. Now, but 1T DRAM cell, which we'll introduce a little bit later, will be destructive read operation. Now let us start explaining the read operation. Let's say we want to read something. Somehow A1 is stored here. Somehow A1 is stored here. Before we explain the read operation, 3T DRAM cell works on a reverse logic. Read will take place to bit line 2. If bit line 2 is going down, sense amplifier will interpret it that I am reading a 1. If bit line 2 value remains high or going up, sense amplifier will sense that it is a 0 we are reading. So it's a reverse logic. Bit line 2 will go down if it is reading a 1. Bit line 2 will stay at powered value of 1 or will go up if it is reading a 0. Reverse logic. So let us assume that A1 is stored here and I want to read it. Read should be done through bit line 2. With A1, M2 is on. With read operation, I have to activate read word line. With activation of read word line, which is connected to M3, M3 transistor will be on. At the beginning of read operation, I have to activate bit line 2. So bit line 2 is now powered up. At the beginning of read operation, I have to power up bit line 2, activate word line, read word line. So this transistor is on, this bit line is powered up. Now if we are reading 1, this one will turn on M2. So bit line 2 will get a connection to ground. So bit line 2 will go down. For a 1 stored here, I am trying to read the value at node X, which is at my memory node. If it's a 1 stored here, upon activation of bit line 2 and word line, this transistor is on. But this transistor, whether it's on or off, depends on what is stored here, right? Because memory node is input to this transistor. If it's a 1 stored, it is on. Bit line 2 will get connection to ground. It will see a discharge. Sense amplifier connected to the bit line 2 will see that bit line 2 value is actually going down for its ground connection. So it will interpret that bit line 2 is actually reading a 1 while it is going down. Now let's look at the other scenario. Let's say I have a 0 stored here. I want to read it. I have to activate bit line 2. I have to activate read word line. M3 is on. Bit line 2 is powered up. It is connected to this transistor. But if I have a 0 stored here, this transistor is off. So bit line 2 will not have a connection to ground. So it will remain at its powered up high value. So the sense amplifier will see that bit line is giving me a 1 because it is at powered up high value. So it will interpret that bit line 2 is actually a reading 0. That's why it's an inverse or reverse logic. That's how reading 1 and reading 0 takes place. Now let us see. So while I am reading 1 and 0, node X value is not changing, because while I am reading node X, I did not activate write word line. So this transistor is not on. So whatever happens here, it will not affect node X. This transistor is on and off based on node X, but node X doesn't get a connection to ground because it is applied to the gate, which is insulated. So the node X is holding its value in floating state, in dynamic state, across this parasitic capacitance effective at node. So it's a dynamic node, while it is storing the value 1 or 0, whatever. It is disconnected from here, it is disconnected from here. It is a dynamic node, but while I am reading this node X through this bit line, the value itself here is not changing, so it is a non-destructive reading operation. Now let us see what happens if I want to write a new value. Writing has to be done through bit line 1. Let's say I want to write a 1 into node X. Right? I will activate write word line. This transistor M1 will be on. The 1 you are writing will be delivered to bit line. So now it will charge node X, because this is now high. It will charge node X, but there is one problem. This is an NMOS transistor. It can never charge it all the way up to VDD. It will charge it up to VDD minus VTH. But the good news is, in memory, we don't want any node to be charged all the way up to VDD. It always works on a reduced swing, right? Even if the internal node voltage is below VDD, as long as it is close to VDD, we interpret it as a 1, close to 0, interpret it as a 0. So it will be charged up. But now if I want to write 0, activate write word line, this is on, 0 is supplied here, so it will be discharged. Right? It will be discharged, so it will be discharged to 0. This is an NMOS transistor, it can discharge it fully. So that is the write operation. Whatever we want to write, we deliver it here, we charge it or discharge it, depending on writing 1 or writing 0, by activating word line to turn on this transistor to provide access to node X. So nobody else can access to node X until this transistor is on. So the node X will maintain its value in floating state. But as we know, we cannot leave a dynamic node in a floating state for a long time, so you have to refresh it periodically if it stays in node. So that is the 3T DRAM cell. But designers were not even happy with this simplistic 3T DRAM cell. They wanted further improvement. Yes, before we move to the next one.
And the refresh circuitry would just be per column, right?
Yeah, so refresh circuitry for any dynamic circuit, that is a separate arrangement we have to have. There's an overhead of dynamic circuit, so we don't show it here. We are just showing the basic design. Yes.
So when we are writing 0 at bit line 1, then the transistor will be off, right? Then how NMOS will act as pull?
No. Every time we are writing, we have to activate this word line, write word line. So transistor M1 will be on. Writing will be done to bit line 1. If you are writing 1, it has to be placed on bit line 1. If you are writing 0, it has to be placed on bit line 1. Upon activation of write word line, this transistor will be on, providing a connection from bit line 1 to node X. If you are writing a 1, it will charge. If you are writing a 0, it will discharge. So, further improvement of this design, they wanted to have a DRAM with the same complexity of ROM. ROM is maximum 1 transistor. So they wanted to have a DRAM with 1 transistor. 1 bit line, 1 word line like ROM, and maximum 1 transistor. The difference between ROM and 1T DROM, that's the introduction of all the current version of DROM you use. 1T DRAM, 1 transistor. What is the difference with ROM? In ROM, sometimes you will have 1 transistor, sometimes you will not have that transistor, presence or absence. In 1T DRAM, you must have 1 transistor at every intersection to store the information, 1 or 0. So we'll explain it Thursday. I don't want to complicate it further. So Thursday we will finish memory lecture, and then I will give you a take-home quiz on memory lecture and a take-home homework on memory lecture, because we don't have time after Thanksgiving to finish lecture 9, right? So we have to use both days, Tuesday and Thursday. So for memory lecture and lecture 9, we will have 2 quizzes, but those will be take-home quiz, and also we'll have an elaborate practice homework so that you can prepare for your final exam, or exam 2. Yes.
The final exam, it's from lecture
Lecture
5.
6 to 5 or 6 to
6.
5, 5, yeah, 5 I believe, 5 to 10.
5 to 10.
Yeah, 6 to 10 or 5 to 10, I can't remember. 6 to 10.
Keep it 6 to 10.
If anything, we are covered right in better when we were.
Yeah.
And
Yeah.
another question is the quiz will have a timetable, like we need to finish it this time.
Yeah, there will be a deadline. There will be a deadline, because I will not definitely give the deadline during the Thanksgiving week. Yeah. So enjoy the Thanksgiving week. And, but we are meeting again on Thursday.
Yeah.